everybody, and thank you for attending today's session, NASA Operational Simulator for Small Satellites NOS Cubed. Please note that this session will be recorded and available on our website in the media gallery afterwards. And we'd like to remind all participants to please turn off their video cameras and mute their microphones during the presentation. If you have a question during the presentation, please type it into the chat below, and a moderator will ask the question to the speaker for you. With that, I'd like to introduce Matt Grubb. So Matt is a senior systems engineer at NASA's Katherine Johnson IB&V facility, and is also lead engineer of STF-1 mission and software engineer for Lunar IceCube and GTOSat. And with that, I'd like to pass it off to Matt for his presentation. Matt?
Okay, thanks a lot. I think I fixed the presentation error. Aaron, could you confirm?
You did.
Okay, great. John, let me know too. I had a wrong screen up. So, yeah, with that, this is a presentation for NOS Cubed. We have recently released version 1.05. This came out on July 10th. So if you're a NOS Cube user and you haven't upgraded, this presentation will cover what is in release 1.05. And I'm going to try and go through it pretty quick so I have time to do a demo at the end and show people the functionality that we have, and then also leave time for questions and show you guys the website and where you can get more information instead of just spending all my time on the slides. So background, we'll go through a NOS Cube background, how we got started. I'll go through the components and the architecture of NOS Cube, the new repository structure. Again, if you're a current user, this has changed drastically. The virtual machine that we provide, how to install, and then I'll go through a demo and like I said, leave some time for questions. So how did NOS Cube get started? So back in fall of 2014, we put together a proposal to launch a CubeSat simulation to Flight 1, with the objective being to develop a simulator that we can use from the time that we start the spacecraft life cycle all the way up until launch and then even on orbit. So we did that. The timeline here, fall 2014 was when we started. We ended up not launching until 2018. And we had our first contact on December 19th, 2018. And we had a contact as recently as I think this morning at 2 o'clock in the morning. So we're approaching 600 days on orbit, coming up on Thursday or Friday. Got my time zones mixed up, but the CubeSat has been highly successful in our eyes, and I would say that is, very, it's very dependent on NOS Cube. We were able to test all these different edge cases and make sure that our flight software was solid before we launched the satellite, and we were actually even able to be done with software before we went to environmental testing, which is rare in the CubeSat realm. So the objective, as I mentioned, is basically to shrink everything that's in this CubeSat, all of your hardware, all of your instruments, all the flight software, the ground station that you're going to use to talk to it, into a laptop to run with, kind of real world data coming from the hardware. So we did that, and this diagram is actually pretty funny because when I shrunk the satellite, you notice that the dimensions aren't the same there. But that's actually kind of a good representation because you're able to do a ton of stuff with NOS Cube, but you're not able to do every single thing. So it's not a one-to-one, but it's pretty close. So what and why? NOS Cubed is a open source software test bed for small sats. We've been released open source for a couple years now. It's a collection of Linux executables and libraries. A lot of these things come from Goddard. Some of them come from other places. So I'll go through the components later. The current simulations that are in there are based on hardware that we're able to open source from simulation to Flight 1. So there's stuff in there like power systems, a GPS, and then there's other things that aren't included from STF-1 that like the radio is an ITAR component, so we can't include it. So we stub that out in a different method. It easily interfaces to core flight system, but we've set up the simulation side of things so you don't have to have core flight system. You could work with something else if you'd like to, but I would suggest sticking with CFS. Why should you care? So especially right now in this COVID timeframe where it's hard for people to get into the lab. I know we're having this problem at Goddard. We can't get, a bunch of people in the lab working on the flat sat like we used to. So with NOS Cube, you can actually do your flight software development in this virtual environment, and you can test with, pretty much real world inputs to continue your testing flight software V&V. You can do different types of stress conditions, fault injection that isn't safe to do on hardware. And we've actually provided NOSCube to our instrument teams, and we've done this both for STF-1 and on some other Goddard missions, where we're able to give them a copy of NOSCube with a virtual spacecraft, and they can, start developing their app and testing it for the science side of things that we as engineers kind of, I don't want to say let fall through the cracks, but we don't know the in-depth stuff that they're going to care about. So they're able to take this and do their own development there. And then also when you're done, you can use this for planning your mission before launch and training. So we were able to use NOSCube a lot while we were waiting in the, that gap in the schedule from when we were done with the spacecraft and when we were actually launching to do a whole lot of, other tests. You can train operators, all that kind of stuff. Okay, so the components that are included, the first thing to get started is Vagrant. This will be the first thing that you need. It generates the virtual machine from the flight software source that you can just go and pull on GitHub. There are scripts to build and run flight software. So the machine gives you a nice, say you have 10 developers on your mission, you have a nice interface. All 10 of those developers can have the exact same VM, ran from Vagrant, and have everything installed in an easy to launch environment. Flight software that's included is CFS. So CFS, if you tuned into either Alan or Dave's presentations previous to this one, you got to learn a whole lot more about CFS, and I won't really go into a lot of CFS stuff, but it is a open source reusable flight software framework from Goddard. It includes an operating system abstraction layer that we leverage heavily for NOSCube. So this allows us to build for your Linux laptop and run everything on Linux. And then it also allows you to build for the flight target that you're going to want to build for. So that's the idea with NOSCube is you build both in parallel, and you end up with one target that you can run on the hardware, either in your FlatSat or on the real satellite, and then one target that you can run on your laptop in NOSCube without changing any source code. Also, you get a ground software. So right now we support 2 ground softwares. AMOS Instrument Toolkit is provided from NASA JPL. This interfaces with the DSNs. So for the current missions that we're working at Goddard, we're not using AIT, we're actually using Cosmos. Cosmos is an open source software provider for Ball. And again, if you listen to Dave's talk or Alan's, you heard a little bit about Cosmos, but it is the the ground software that's used on STF-1. It's also the ground software that I'll show in the demo for NOSCube. There it goes. Okay, the other components, NOS Engine is a middleware developed by the JSTAR team at NASA IBNV. So we use this on other projects. It's designed specifically for simulation. You can do time synchronization. You can do data manipulation here, so you can grab a message off the bus, change it. You can do fault injection. Currently, it supports I2C, UART, CAN, SPI. In a future release, we'll have GPIO and a generic memory interface for accessing memory registers in an FPGA or maybe some other sort of memory location on your board. And this is the glue that ties everything together in NOSCube. And we also have a suite of hardware models and a framework that we've developed to generate new models. So there's a nice sample application in there and a sample simulator that you can use to start from when you're developing new things. And then you can use all these other models as good examples for different sorts of things. So we try and reference this in the documentation. But if you want to do a streaming device like a GPS that's going to constantly stream data, it's good to look at the Novatel GPS component in simulator and use that as an example. Whereas it's something like a reaction wheel, where we provide a generic reaction wheel that you can use to then edit and make into a real reaction wheel simulator, like if you were using a Sinclair wheel or a Cube wheel or whatever it may be. Then 42 provides us our dynamics environment. So 42 is another GSFC developed open source component that you can use separately from NOSCube, but we include it in here and link it all together. It gives you visualization, so you can see a couple pictures there. Shows you where your satellite's at in orbit, and then gives you a nice visualization of the satellite and maybe how it's spinning, what the orbit dynamics look like. And we time synchronize 42 with NOS Engine, as well as CFS. Everything gets time synced together. And 42 is used for components that are going to provide you real world quote data, something about the environment that the spacecraft's in. So we use 42 for all those pieces. All right, this diagram gives us a pretty good view of what's happening on the computer. So in your computer, you have Cosmos running, it's talking over a TCP IP socket. Actually, in this case, I believe it's set up for UDP now. But it's talking to your flight software, CFS, and it's using the CI and TO applications that we use for the actual flight mission. So Cosmos talks directly to your flight software, and then through NOS Engine, flight software talks to this whole suite of your simulated satellite hardware. So your GPS simulator, your magnetometer simulator, blah, 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 whatever else is in there. And then those sims separately connect to 42. So you get a whole stream here, kind of end to end how this is going to look. Then in the virtual machine, you can either share the NOS source through a shared folder. That's what I do. It's what most people do. But you can also generate the virtual machine and then clone the source, directly into your VM. Now, the magic in NOS Cubed here is kind of shown in this diagram. So I mentioned you can generate the code for both targets at the same time without having to change any background in the flight software. The flight software that you generate for NOS Cube is going to think that it's the same as the flight target. And how we do that is through the platform support package in the hardware library. We actually tell it at compile time when it's generating for the NOS Cube target that we want to use a NOS Engine compatible hardware library. Whereas when we're building for flight, we're going to want to do whichever our target may be. So in the case of STF1, it was an AVR32. So we had a hardware library for the AVR32. Now on the NOS side, the hardware library is going to implement drivers that talk to NOS Engine instead of the drivers that actually would talk to either a UART or an I2C. But the communications is still byte by byte, just like it is if you're using real hardware. So you get, a very good representation of how the hardware would communicate when you're using NOS Engine. So everything gets passed through the engine server, and you can have a suite of all of these simulated hardware clients, as I mentioned. And then another thing that we don't support all the time, but comes up, is actually plugging a real piece of flight hardware into the NOS target. And that's what is shown in the right side of the tree here, where you can actually write a reverse NOS driver that converts the NOS Engine message to a real UART message and is able to talk to, say the GPS if you wanted to plug in a real GPS to your simulator. Okay, so this is a big thing that's changed since we first started NOS Cubed. Everything was living in one repo. It was all combined together. We didn't really have a good way to get upstream updates like from CFS or from 42. So we reorganized everything. Everything is now in a submodule that links to the open source package. And then we also have submodules that link to all of our NOS 3 packages. And we fork these repos from the original source if we need to make additions. So in the case of like the platform support package for CFS, we have our own NOS Cubed PSP that we've written. So we forked the PSP from the latest upstream release, and we added that in. So, you can't just pull CFS directly and have it be compatible with NOS Cube. We've done all the work for you so you can, get started really quickly. So in the repo, you'll see 4 main folders. So there's the deployment folder, which is the repo that you start from to generate the NOS Cube virtual environment. And there's a README in there that tells you how to do everything. It's pretty simple. There's a flight software repo, which is the CFS 6.7 release, all of the CFS released apps that we support, the NOS 3 component apps for the hardware that we support, and the build system. Then there's a simulator folder, the sims folder, which has all of the NOS 3 configuration, all the component simulators, all the NOS Cube tools, the generic code, the sample apps, stuff like that. Then there's a ground software folder, which has the Cosmos config and definitions, the AIT config and definitions, the scripts that are used to do all the launching, and then some other ground-based tools. So to get started with this, it's as simple as do a git clone of nos3.git here. Again, this is open source. You can just pull it right from GitHub. Change directory into the NOS3 directory. You init your submodules, update your submodules to pull the latest code, and then you follow the instructions in the deployment README, which is just performing a vagrant up from the deployment folder to generate your VM. Okay, so now onto the VM. As I mentioned, the deployment folder here is where the Vagrant and Ansible code lives to generate the virtual machine. Ansible will actually install all the tools necessary. There's nothing you got to do yourself. It'll install NOS Engine 42 Cosmos. It does not any longer, this is one change that we've made, it does no longer copy the code into the VM. You actually need to create a shared folder or install Git and clone the source for NOSCube into the virtual machine. And that's really so you can source control your own changes to NOSCube. In the past, when you just copy the source into the VM, any changes that you make, you have to then, do something to back them up and use version control. Went one too far. Okay. I mentioned this earlier, that getting started for the deployment repo is as simple as change the directories to deployment, do a vagrant up, and wait. And I'll emphasize wait. Depending on your internet connection, this could take anywhere from 20 minutes to 2 hours. Depending on the time of day I've done it, I've seen both. So keep that in mind. It will tell you when it's done. That's one of the main questions that we get is I can't log into the VM. I don't have a GUI for the VM. Pretty much any errors that you see in the very beginning come from the Vagrant process when it's generating the VM. If you lose connection at any point, it will hurt you and you'll have to redo this. So definitely wait. So in the VM, Cosmos is installed in its default directory, and it actually now gets ran from your source location. So this also allows you to version control your Cosmos tables. So another really good feature in this new release. 42 is installed from Git now, instead of being installed from a package, which we were doing in the past. It gets installed to op42, but the config files actually live in your NOSCube repository. So again, those can be version controlled, good feature. They get copied into the location at build time, so you're actually able to run your NOSCube version in 42. NOS Engine is installed as a Debian package, and the standalone server can be found in user bin. You don't really have to worry about this unless you want to run it yourself. The launch script will call it for you. And I mentioned this, sources in the VM. You got to do that yourself. So to build and run, I notice I got a typo there, but the make file wraps everything to make this as simple as possible. You call make to build everything, make launch to run everything, make stop to stop everything, and then make clean to do a clean build. So that's all you have to worry about for running, building, cleaning up NOSCube. All right, awesome. So I got through the slides. I guess I'll do a quick break before I start the demo. Does anybody have a question?
Or will you be sharing your slides, or should we just send you an email?
So I will have my email at the end, and Aaron, I believe that the slides will be posted.
We will be posting a recording of this in the media gallery. There's a webinar archive, so you'll be able to find that in about 24 hours after this session ends. I'll post the link in the chat.
Thank you. I was asking for the charts, but you were asking about the video, so thank you.
Yes, and if you'd like, you could email me, and we can provide the charts too. So let me just change my screen here to share the virtual machine. Does not seem to want to work. Okay, there we go. Now I can share my VirtualBox. Okay, so this is the VM that you're going to get when you generate from the Vagrant script, and you just log into this with the password that's included in the README file. And I've actually already got my shared folder set up here to save time. So in this shared folder, I don't want to do a make build because it'll take a little while. But I will just do a make launch so you guys can see this running. And I'll give it a second to start everything. Okay, so what all do you get? This looks a lot like the OpenSat kit that Dave was showing earlier in terms of the things that are included. But here on the right side, we have the Cosmos launcher. So I will go ahead and boot up our command and telemetry server. Again, this is now running from the config files that are actually in the NOSCube source. So I will boot up that. And you'll see we have a connection here. So Cosmos is connected to the CI and TO interfaces of CFS. Then here we have 42 showing us where our spacecraft is. Here it looks like we're in the dark on the map. I'll just minimize these to get them out of the way. All right, and then we have our NOSCube flight software now in the middle of the screen, so you can see that CFS has booted. You'll see these start and stop flywheel messages. What these are is the minor frames are not in sync on this Linux machine. So as I mentioned earlier, one thing that NOSCube doesn't give you is a perfect one-to-one. So on hardware, you're going to have either a real-time clock or an oscillator-driven clock. On here, we're just running from Linux, and since there's so many processes running in Linux, sometimes we'll skip major and minor frames. This is actually something we're looking at enhancing in a future version to get some better time synchronization when everything's running together. But if you see start and stop flywheel, it's not an error, and it's not really hurting you, but the message is typical. So flight software here is running. Then on the left side, again, another 42 window showing you the data that 42 is outputting. Minimize that. And then here we have a large terminal with many tabs, and this is all of the simulators that we're going to be using. Okay, it doesn't want to go away. So we have NOS Engine here running. You can actually look and see which buses are connected. So there's I2C buses, UART buses, SPI buses. You can query the data nodes that are connected to those buses. So in this case, I2C 0 has 4 things connected. You'll see this command bus. The command bus is what we use to command the simulators to inject faults if we want to do that. And it's also used to provide time to all the different simulators and sync things together. Again, UARTs are connected. You'll see the time driver window. This is our time sync that's sending ticks to everybody so that they get a consistent time tick and they can run in sync. Sim terminal, I mentioned, that's our way to inject faults. We provide a sample simulator here, which in this case is just providing data. It's just streaming data. A battery simulator and a power system simulator. The camera simulator is in, so this is a good example of using I2C and SPI communication. The GPS simulator here is based off of a Novatel GPS, but this is a very good example for a streaming device that streams over a UART. So all these things are included here. And just to show you guys, a quick way of how you would use this, you're actually using the same interface that the ground operators would use. So this Cosmos interface is the same thing that I use to talk to STF1. And we'll just want to boot up our command sender. Okay, and I want to pull back up flight software just so we can see it getting commands. All right, so the first command that I always send is enabling telemetry. So by default, the telemetry output application is not dumping telemetry. So I'll go ahead and send that. You'll see it gets received by flight software here. It enables, and you'll also see my Cosmos bytes received starting to tick up. So as telemetry is coming in from CFS, Cosmos is cataloging it here, and you can view EVS packets, whatever other packets you want to look at. But one of the very cool new features that we added in this release is the ability to actually command actuators in NOSCube. So in previous releases, we only had the ability to get telemetry from sensors in 42. Now we can actually command the spacecraft to do slews and change its attitude. So I'll do that now with the generic reaction wheel. So the first command here is just a no op. send the no-op. Okay, my app's alive. Flight software got the command. Everything looks good there. And then I will request data to see what my current values are. And okay, yep, got a data packet in Cosmos. So if I want to view that, pull it up. And you can see right now, the wheel's not doing anything. There is no momentum on the wheel, but say we want to command the wheel. So I will set the torque here to something high, and 4 Newton meters per second will probably saturate the wheel, but we'll send it anyway. Okay, and you can see flight software gets it, torque command received. And if we actually look at 42, we should see the satellite start to spin up. And it is slow, but as that wheel accumulates momentum, this thing will start to spin faster and faster. And to get that data again, to see what our current momentum is, we can just request the data packet again. And you'll see it's starting to build up momentum here. And if we continue to request it, it's going to keep growing. So that's the coolest new feature that we've added in terms of flight software and testing. It was something that folks asked for a lot in the past, and we just didn't have the functionality yet. But with newer versions of 42 and with the newer version of NOS-Cube, we're actually able to do this. So we can command the reaction wheels to spin up. And again, this is maybe a bad example. You never want to just turn on one reaction wheel and set your spacecraft spinning, but it shows the functionality is there. So if you want to develop your own attitude control algorithms, you can do that in CFS and then see it working in 42, and then also get all that data to the ground to analyze later. So where NOS-Cube differs from the OpenSat kit and the PySat that Alan Cudmore developed is this is more or less looking at developing your flight software for your mission. It's not necessarily a learning tool. It can be used as a learning tool, but it's more meant to pull this as your starting point for a mission, simulate your spacecraft with our simulator framework, and then start developing your flight software and testing your flight software and your ground tables to make sure that everything works so you're ready for when you're on orbit. So it's a little bit different of a use case. And I actually think it would probably be useful to have OpenSat Kit as your starting point, learn about CFS, figure out how to write apps and do all those things, and then come into something like NOS-Cubed and actually start developing your software and testing your software and just driving up the reliability there. As I mentioned, for STF-1, we haven't had any flight software anomalies. We've had some things that we've had to fix in terms of hardware going bad over the 2 years that we've been on orbit. But NOS-Cube was very instrumental in our flight software development and our test campaign just to make sure that everything was ready. So with that, I'll just stop this and I'll open up the floor to the discussion. And let me also just share my last slide here so you guys can see the website. Sorry, my internet's a little behind with running WebEx. So if you go to the website here at the end, it doesn't look like it's sharing. Well, in that case, I'll just pull up the website. That'll be easier. Okay, there we go. So github.com/NASA/NOS-Cube. You can use the issue tracker here to submit questions and issues. You can pull the code. There is a release package. If you go over here to releases, that has the user's guide as a PDF. And then we also provide a interactive user's guide. If you go to nos3.org, it actually forwards you to our STF1 page, but nos3.org will take you to the main page of our documentation where you can actually click through and view the user's guide in a page-by-page basis instead of trying to do it through the PDF. So are there any questions?
So Matt, yes, we do have a couple questions here. What about translation control? Does NOSCube support maneuver modeling?
It does. The maneuvers and the actual algorithms are going to be up to the developer, the flight software developer, the ACS software developer. So you have a reaction wheel included. It is generic, so you would want to change that model to be the actual reaction wheel that you're going to talk to. And you would also need to add whatever other components are used in your algorithm. If you have star trackers, magnet torquers, sun sensors, those things. All the functionality is there, but again, this is the open source NOSCube is kind of like your starting point. So we give you the examples to build up, a full simulation.
Okay, great. And another question is 42 configurable with a working CAD model and mass properties?
Yes, it is. So by default, our configuration is stored in this config folder. So you'll see these input files here. Hopefully my screen's still sharing. But these config files are the 42 configuration files. So you can actually upload your own spacecraft file, such as this spacecraft here is our NOSCube spacecraft, but you can upload all of your own body parameters into 42. So yes, that is available. And then as well as the spacecraft model itself is the NOSCube model that we're using now, but you can also provide your solid model to 42 so you get realistic drag and such. And I also missed the word translation. 42 does support thrusters, if that helps answer the previous question.
Great. And then we have what makes NOSCube simulator being for small satellites different for traditional satellites?
There's not a lot. So the main thing that differs in the way we do NOSCube for small sats and the way we simulate large satellites is we're running NOSCube on a Linux virtual machine. So it is cross-compiling the code for Linux, whereas on the larger satellites, we would run a product like QEMU or Symix, so we could run the actual source code. Those are a lot more development time to develop your models for the actual processor, whereas small sats, you typically just acquire a processor from a company. And if it supports Linux, that's good. If not, you can cross-compile in NOSCube. But the main difference is there that we don't use any paid products for NOSCube, so we're cutting down on cost and time to spin up to get you moving, for the small sat life cycle versus the large mission life cycle where there's, many years of development and preparing the simulators in parallel with, developing the flight software.
Great. And there was a follow-up to that. Are there limitations on the thruster or maneuver modeling? For example, can low thrust finite maneuvers be modeled?
So as far as I know, the thruster is configurable for whichever thruster that you are modeling after. So you give it your maximum thrust, and you would model, if it's a cold gas thruster with a specific impulse versus, an ion thruster that's going to speed you up over time. It would be up to the 42 model that you create for your thruster. But in terms of those questions, Eric Stoneking, who developed 42, may be able to answer a little bit better if there's anything, any limitations in his implementation in 42 that could cause issues. But as far as I know, everything in there is configurable for what you would want to model. And we've actually modeled, the ion thrusters in one specific case in 42.
So anyone have any more questions? So there don't appear to be any more questions at this time. So
Great.
with
If you
that,
do have any other questions, feel free to reach out to me or reach out here on our GitHub page, or if you actually go to the documentation page here, you can click the help tab and there is a support@nos3.org email. This doesn't get monitored quite as much as the GitHub, but you can also email us directly right here at support@noscube.org.
great. So we did get one more question: is would it be possible to run from Ubuntu without a VM?
In the past, that was a specifically supported feature where you could run NOS cubed in your VM. Now it's 100% possible. The best bet for that would be to just follow the steps that are in the Ansible script and do that on your Ubuntu host. So it's not as easy as generating the VM, but if you look in the deployment repository in Ansible, you can actually see the tasks that we're running. So you can see the 42 task, how we install 42. The ground task shows you either how to install Cosmos or AIT, the way that we do it, so it goes in the right place. The software environment, this is all of the packages that we need to install, for the GUIs and different things. So yes, you could definitely follow the Ansible tasks that are here and generate, a very similar environment in a Ubuntu host. So you don't have to generate a VM. So good question. Not quite as easy as the old way that we did it, but this is a much more robust installation process than we had in the past.
Great. Any more questions to come in? I can see that Aaron has pasted in Matt's email below. So, and also the support address for him as well, for NOSCube as well.
Great. Yeah. If anybody comes up with any other questions, or if you pull this code down and get a chance to use it and come up with any issues, as I mentioned, just reach out to us.
Sounds great. And with that, we'll go ahead and end the recording. Just want to say thanks to everybody, Matt, and to the attendees for coming in. And again, this recording will be available tomorrow at the Media Gallery. And that will end us.
Great. Thank you, everybody, for joining.
Thank you.